Unlocking the secrets of Chernobyl, tiny fuel grains tell a big story. Imagine holding a piece of history so small you can barely see it, yet it holds the key to understanding one of the worst nuclear disasters in history. Scientists have done just that, extracting vital information from microscopic fuel grains found near the Chernobyl site. These tiny fragments, smaller than dust particles, are like miniature time capsules, preserving secrets about how the damaged reactor operated. Inside these grains, researchers found trapped radioactive gases, including Krypton and Xenon, which were produced when the reactor's fuel atoms split apart. By analyzing these gases, scientists can reconstruct the fuel's age, the intensity of neutron bombardment it experienced, and even whether uranium or plutonium dominated the reactions. Microscopic messengers, the legacy of Chernobyl. After the Chernobyl accident, the reactor core scattered hot particles, microscopic bits of radioactive fuel, across the surrounding landscape. These particles, many just a few micrometers wide, have remained in the soil and sediments near the plant for decades. This groundbreaking research was led by Laura Leifermann, a nuclear chemist at the Institute of Radioecology and Radiation Protection at Leibniz University Hanover in Germany. Her work focuses on these radioactive fuel fragments and what they reveal about reactor behavior. Challenging assumptions. What did we really know? The conventional wisdom was that the intense heat and fire of the accident would have stripped these grains of their fission gases, leaving only solid residues. But the team set out to challenge this assumption by examining particles from the Chernobyl exclusion zone. Earlier lab work had shown that analyzing multiple elements in similar particles could reveal how the fuel burned and weathered over time. This method used resonance ionization mass spectrometry, a laser-based technique that measures selected isotopes with minimal damage to the particle. Gases tell tales, peering into the past. The team selected particles from soil and sediment samples collected inside the Chernobyl area, where access is restricted for safety reasons. To get a closer look, researchers used a focused ion beam, a tool that slices solids on a micrometer scale, to cut each particle in half. Electron microscope images revealed sealed pores and grain boundaries, forming a closed internal maze. Researchers then heated the particle halves in small steps under a vacuum, capturing the released gases and analyzing them using noble gas mass spectrometry. The study found clear Krypton and Xenon signals from micrometer-scale particles that had been in the environment for over 3 decades. But here's where it gets controversial. This discovery challenges earlier official assessments that suggested most noble gases were fully released during the accident. Reading the reactor's history, a clock inside the fuel. The Krypton and Xenon trapped within the fuel grains record isotopic ratios, which create unique patterns for each type of fission. In this study, most particles showed signs of low-enriched uranium fuel, matching the burnup used in the Chernobyl reactor. The clock inside these gases relies on radiochronometry, using radioactive decay to estimate how long ago the fuel left the core. A recent method shows that Krypton 85 ratios can date spent fuel with enough precision to track its operational history. The Chernobyl particles showed Krypton 85 levels consistent with irradiation between late 1981 and late 1985, just before the accident. These ages align with the expected residence times of fuel rods, which typically spent about 3 years in the reactor. Xenon isotopes also provide information about the thermal neutron flux, the intensity of slow neutrons moving through the core during operation. For most particles, the Xenon data match the expected patterns for the RBMK design at Chernobyl, linking each grain to a specific fuel environment. The Nereus particle, an intriguing anomaly. One particular grain, nicknamed Nereus, stood out. Its Krypton and Xenon ratios suggested a much larger share of plutonium fission than the others. Its composition indicated a medium burnup, typical of other Chernobyl particles. The most likely explanation is that this fragment was located near the end of a fuel rod, where neutron fields are weaker over longer periods, potentially leading to increased plutonium production. The researchers also checked for atmospheric contamination, but found almost none, suggesting that the unusual pattern in Nereus reflects genuine differences in its reactor history. Nereus demonstrates that even 2 grains from the same assembly can have very different gas records depending on their exact location in the core. Lessons from Chernobyl fuel. a new era of nuclear forensics. The field of nuclear forensics analyzes nuclear materials to determine their origin. Xenon and Krypton signatures are a valuable part of this toolkit because they can identify the reactor type and operating conditions. Trapped gases in individual grains provide even more detail, allowing analysts to link particles to a specific reactor design and a narrow operating window. Because this method works on micrometer-scale particles, it can be applied to environmental samples or seized powders without requiring large amounts of material. From an environmental perspective, the primary risk from these grains comes from the solid radionuclides embedded in the fuel matrix. The remaining noble gases, like Krypton and Xenon, are mostly trapped in sealed pores, and many radioactive isotopes have already decayed. And this is the part most people miss. Together with earlier multi-element studies, this research shows that tiny fuel grains can serve as durable records of reactor behavior. Reading these records offers new ways to trace nuclear materials, verify safety claims, and understand how accidents leave lasting marks on the environment. Controversy and comment hooks. What do you think about the implications of this research? Does it change your understanding of the Chernobyl disaster? Do you believe this technology could be used to improve nuclear safety or uncover past nuclear events? Share your thoughts in the comments below.